All right, hope everybody had a good lunch. So I thought I was wrong once, but I was mistaken. So before lunch, we were a little confused about load and store. Apparently everything is running right. I double checked it. ChatGPT lied to me before lunch. So just to be clear on load and store, it's a little bit confusing looking at the code here because you see the store instruction and the load instruction, which are both using X0 as the base register. Looks like they're in different positions. Load has a destination register, store does not. So for the load, this X15 is the destination, this is source 1. For store, this is source 1 and source 2. So these are, X0 is source 1 for both of them. In both cases, that's the base register for the address. So since I was confused about that before break, I just wanted to talk it through and clarify. Okay, did anyone have an epiphany over lunch? Any questions? Okay, so we're going to switch gears now, and so module 3, design team, roles, tools, flows, methodologies. We'll start with a little about silicon fabrication, talk about design teams, what the roles are on the design teams, what each of those roles is responsible for, how they work together. We'll talk about the design tools that are involved in, we've been focused on writing the RTL. We have to get that RTL implemented. What are the tools involved in that? Talk a little about technology trends in the industry and design flows, methodologies, languages, right? We've talked a little about that. And especially you've been introduced to TL-Verilog, but just to relate that to other things. So silicon fabrication, here are some wafers. These are from my own personal collection. I brought these around to other workshops, but I didn't care to fly them to Bhubaneswar. And one of them I actually broke on day one of the first first course that I conducted. So I learned a little bit about the actual physical strength of these wafers. Pretty minimal. I'm going to start out by not talking. We have this video from Matt Venn, who is the force behind Tiny Tape Out. This video is Matt Venn doing a lab tour, so I thought it would be nice to use this video so you can get introduced to Matt Venn, who's the person behind the technology that you're working with Tiny Tape Out, and also get a nice tour of a fabrication facility and a little lesson on how chips are made. So I'm going to start that. Just to check with the recording, Ian, do you know if the audio from the computer here is going to carry through? We'll try it and we'll see. Cross your fingers, hopefully we will be able to let this play.
However you're watching this video, inside the device.
Okay, let's, how do we control that?
This will be lots of microchips. Microchips are the most advanced thing that we make, and it takes an enormous amount of people, equipment, and special chemicals from around the world to make it happen. Normally, it's really difficult to get permission to film inside a clean room. But today at IHP in Frankfurt, Germany, I'm going to take you on a special, exciting tour of their clean room. So let's go and see what it takes to turn a blank wafer like this into one full of microchips like this. Hey, Sebastian.
Hey.
Good to meet you finally, face to face.
Welcome at IHP.
Thank you. So you're the person at IHP that knows all about how everything works, right?
Almost everything.
Because there's so many processes involved, right?
That's right. We are about 500 people here at IHP. And in the clean room are working process engineers, operators, and maintenance staff.
So I'm really excited to go and see inside the clean room. What do we need to do to go and take a look?
We need to dress up.
Because the structures on the chips are so small, less than a millionth of a meter, it's easy for a spot of dust or hair to ruin a wafer. That's why we have to get dressed up in special clothing to go inside. And by special clothing, I don't mean clothes for a Met Gala, although I admit doing our work in a Karl Lagerfeld uniform would be pretty sick. Instead, we wear these special clothes. Don't worry, you don't have to iron them, you only have to hold up the sleeves to stop them touching the floor. It's also pretty noisy because they use a lot of fans to keep the air clean, 1,000 times cleaner than an operating theatre in a hospital. As we go up the stairs, air blows in from the left and the right to remove any last specks of dust. Before we enter the clean room, let's take a step back and understand what we're making. I designed this chip to show the time on a TV screen. Inside the chip are hundreds of logic gates joined together into a circuit. Here's one of the simplest gates, an inverter. When the blue input is low, the orange output goes high. It works by using a pair of switches called MOSFETs. They don't have any moving parts, so they can be made incredibly small. At IHP, they make the MOSFETs so small that you can easily fit 10,000 across your fingertip, or 1,000 if you've got very tiny hands. Here's what one looks like from the top and from the side. We build them on top of a disk of silicon called a wafer. These two areas here are called the drain and the source, and this is called the gate. When a voltage is applied to the gate, it allows electrons to flow from the source to the drain. You can see that as the blue voltage increases, more and more orange current is allowed to pass. Building a whole chip involves repeating hundreds of steps, so we'll just follow the process of building this one MOSFET and its connections up to the first metal wires. Okay, enough of the theory. I hope you're still here and didn't close this video to watch TikTok, or worse, YouTube Shorts. Let's enter the clean room at IHP and meet the people and the tools who build billions of these tiny structures 24 hours a day.
Welcome to our IIT clean room. It has a size of 1,500 square meters, and we operate it for 7 days a week for 24 hours a day. And all in all, we have over 100 tools to produce our integrated circuits. The first thing is that they clean the wafer. So they use different chemicals, for example, to clean it from organics, from oxides, from particles. So a batch of wafers containing 24 wafers is immersed in an etch bath.
In the cleaning and wet etching section, they have 14 different tools from 9 manufacturers. These tools can handle whole boxes of wafers at once, or just work on a single wafer. My favourite part of the cleaning process was seeing them spinning around in this silicon tumble dryer. Dryers are used for wafers, but technically they should work to dry any type of underwear. Unfortunately, I couldn't convince any IHP engineers to test this theory, so I had to confirm with the wafers. After the cleaning, the wafer gets a very thin protective layer out of silicon dioxide, and that's done in a furnace. So the temperature is raised up to 900 degrees C, oxygen is introduced, and this oxygen reacts with the silicon surface and forms a silicon dioxide layer. Next, we use a process called chemical vapor deposition, or CVD, to build up a layer of polycrystalline silicon on top of the oxide layer. Polycrystalline silicon, or polysilicon for short, is silicon but without the perfect crystal structure of the wafer. In other words, polysilicon is the wafer's unemployed brother, and I will stick to that definition until someone comes to give me a better one. I won't answer that. So far, every process has affected the whole wafer evenly. Now, to start building the MOSFET's gate, we only want to remove the oxide and the polysilicon where there isn't a gate. Photolithography is the fundamental technique that allows us to print millions of MOSFET gates in a single intense flash of light. Because photolithography uses light-sensitive chemicals, the overhead lighting is yellow, giving us that classic semiconductor cleanroom vibe. We put a light-sensitive resist on top of the wafer, and for that we use a spin coating process. And there the wafer starts to spin and the resist is spread very even across the wafer. We take the wafer together with a mask containing our structures and we load it into the photolithography machine, and they are aligned to each other, and then light is used which travels through the mask and the lens system which projects the mask 4 times smaller onto the wafer.
This is a photolithography mask. This is quartz glass substrate with a thin layer of chrome on the backside, and we also here see a frame with a very thin foil to avoid particles being placed on the chrome, which we would see when exposing, which would lead to imperfections like short circuits or interrupted metal layers. And on this reticle we have 3 different masks we can use for exposure for 3 different layers.
Okay, and which layer is this?
Those two are 2 top metal layers.
Okay.
And
So that's why the structures look so big.
Yeah, exactly. That's why you can see relatively much on this reticle. And we also have, there's a lot of chrome here, so you can see structures. We have very bright radicals, like a lot of glass and very little chrome. And we have very dark radicals, like a lot of chrome and very little open spots in the chrome. This is the I-line stepper. Yeah, we have an I-line stepper and a DPV stepper, 365 nanometers exposure wavelength. And this is 248.
Okay.
This uses laser, this uses a mercury lamp. Yeah, this is for like the more buff structures, the bigger ones, like top metal, the last few layers, where we have like 2 micron broad of our metal layers. And this is enough for that exposure. We don't need to use this. Usually you only use the tool that is suitable for the job, but it's the least expensive for what you are doing. Okay. That's kind of like the efficiency part behind it. And so that's why we have an I-line. We just call it I-line. It's an SF150 NSR 7 repeat system from Nikon. Yeah. And over there we have, as I said, the DPV stepper, step scanning system that we use for our smallest structures, for the critical layers, especially. That's what this tool is for.
So I just saw the wafers rotating.
Right.
Why is that?
The wafers have a notch which corresponds to the wafer crystal orientation to always align the wafer and expose it or kind of process it inside the tool always in the same kind of way.
Wow.
Kind of a simple system like this, just small line, and it kind of just
the machine finds the line,
Yeah, exactly. Okay.
Which is the most expensive machine in the room?
The one over there, the big one. That's our DPV stepper. Oh, I don't know the exact numbers. I just know it's double digits in the millions.
Yeah. Okay.
Yeah.
After the photoresist is exposed to light, it changes its structure, and then we can develop it so we can remove the exposed regions. Once we have the patterns, the photoresist acts as a mask, and we can do the etching then. So to etch our deep trenches, for example.
This is a reactive ion etching tool. So here we are in the maintenance area of the clean room. In these kind of tools, we etch away material, as the name says, and we do this by creating a plasma above the wafer. We have reactive gases above the wafer. They get ionized in a plasma, and the way it's constructed is such that the plasma can react with the material that we want to etch away. And the special thing about plasma etching is that we can actually control the geometry of the structure. Unlike in
very
steep sidewalls, or actually we can control the sidewall angle. And this is in contrast to wet etching, for example, because in wet etching, when you dip the wafer into the chemical, it etches in all directions, which is called isotropic etching. And of course, if you want to create very small structures, it's not suitable. So that's why we have to use plasma etching.
Right. Yeah. That's like the top view. We just saw that robot.
Exactly. So it's a schematic of the tool, and then we can click around on the buttons here, and we see overviews of the individual chambers with all the different process parameters. So you can see there's a lot of gases installed. You have to monitor different temperatures.
Yeah.
And everything has to be in a specification.
And this is the one where we just did the
this
CVT.
is CVD tool, and then we have also additionally 2 etching chambers in this chamber.
Okay.
And yeah.
Okay, so it doesn't just build up; it can also etch away.
We can actually build up something and then immediately put it to the other chamber and etch it away again.
Wow.
So it's like of a combo tool, if you want.
Handing.
Yes.
Just like my 9-year-old nephew's birthday party, the chemical vapor deposition machine contains a lot of different gases. In the machine's case, it needs them. Those gases are all piped up from the infrastructure floor below the cleanroom. This is also where the chemicals are stored, the water is cleaned, and waste products are made safe. It's much noisier down there, and even more packed with equipment. To continue building our MOSFET, we're going to start repeating steps we've already seen. First, we go back to the cleaning to remove the developed photoresist. Then we repeat the photolithography steps to end up with holes in the developed photoresist. We're left with a structure like this, ready for us to visit a new machine in the factory.
In the ion implantation tool, the wafers are loaded and then they are placed on such a big wheel. And then ions are accelerated. It's like a beam. That's what you see here. And they're accelerated towards the wafer and then implanted into the wafer. And we use different materials or different ions. We use phosphorus, arsenic, and boron mainly.
And with the machine, you can choose which type of ions and how deep to implant them.
Right. We separate them according to the mass, and with different energies, we can choose the depth of the implantation.
And what is the concentration of the ions into the silicon?
It's really different. Depends on the application. Let's say it's from 1 dopant per 100 silicon atoms up to 1 dopant per million silicon atoms.
So a really big range then.
It's a really big range, yes.
If you're a fan of particle accelerators like me, first, know that everything is going to be okay. You'll be okay, people love you for who you are. And second, check out the time I used a synchrotron to make a 3D X-ray of my clock chip.
After the ion implantation, the silicon is pretty much damaged, so we need to heal it. And to heal the silicon, we use a process called rapid thermal processing. It's called RTP. And there, the silicon is recrystallized, and also the dopants are electrically activated.
Now that we've finished all the steps to build the active part of the MOSFET, the next part is creating the metal wires that connect up all the MOSFETs into the bigger circuit. To start, we grow a layer of silicon dioxide over everything, which results in a bumpy top surface. We want it smooth, so we're going to grind it extremely flat using chemical mechanical polishing, or CMP.
So we have two sides on it. One side we do oxide, removing the oxide, ILD, STI on one side. On the other side of it, we do tungsten.
Okay, removing tungsten. There's two different processes.
Yeah, a little bit. And the recipe is different, and also the slurry we use is different.
Okay.
Yeah, that's the main thing. So I'm just done with the process right now.
Okay.
But I can start the process if you want to see.
Yeah, that would be amazing.
Okay, it's good. I can start it.
Start the process.
The warm-up wafer comes in twice. Then the real wafer we're going to...
Oh, so you have like a dummy wafer.
Exactly.
Okay.
So the dummy wafer comes
Yeah.
first to check the process.
Yeah.
Once the process is fine, once everything is good,
Okay.
you can send the wafer can come.
Okay.
Once the process is not good or something like that, you can abort the process. It's just more like I feel like it's like a safety.
Yeah, I
safety
like it warm-up wafer.
Exactly.
It's cool.
Warm-up wafer. That's what we call it.
When I'm looking at the polishing, I'm seeing like this little spark of light. What's
Yes,
that?
that's the optical endpoint. Yeah. When the wafer reaches the limits at which the polish limits or the desired limits, it stops automatically and transfers to the next process.
Okay.
That's basically the goal.
All right. And then this is coming to dress the wheel again to kind of clean it, clean away that.
Exactly. So after using the tungsten CMP, I have to check if there's tungsten rest on it. For this particular process right now, you can see some white cloudy stuff on it here. So there's tungsten on it. You can see there's little tungsten on it. So I have to see what to do to make sure everything is...
Needs to go back in the machine.
Yeah, probably.
For longer.
Yeah.
So you're aiming between not enough and too much, and you've got to get it just perfect.
Exactly.
Wow.
Exactly.
Our wafer then returns to photolithography, plasma etching, cleaning, then tungsten vapor deposition for the vertical connections, more polishing, aluminium vapor deposition for the horizontal connections, photolithography, plasma etch, and finally cleaning the developed photoresist. All of this has just taken us up to the first metal layer. IHP's process has 7 metal layers, so to finish the wafer, they'll have to repeat all these back end of line steps another 6 times. You might have noticed that the wafer boxes have different coloured clips. A yellow colour means it's for internal testing. The red colour means it's a hot lot. A lot means a box of 25 wafers, and a hot lot means your box doesn't wait in a queue, it's always jumped to the head of the queue of the next process. That saves time, but it does cost more.
To build a whole wafer, it takes about 600 steps, and that takes 3 to 4 months to produce a whole wafer. Once we build up all the layers, the final step is a passivation out of silicon dioxide and silicon nitride, but there we still have to etch some holes to connect our integrated circuit. After all these process steps and all this waiting, the wafer finally comes out of the cleanroom and is diced into little pieces and ready for use.
After the wafer is diced into individual chips, they're normally encased in a plastic package, making them easier to handle. I mentioned earlier that it's very rare to get a look inside a foundry, and that's because the semiconductor industry doesn't want to share its expensive secrets. As well as IHP letting us look inside their factory, they're also letting us look inside their PDK. That's the library of all the things you need to know to actually design a chip. They're part of a growing movement that's making semiconductors more accessible to everyone. In 2024, IHP plans to let amateurs like you and me get our chips made here. And if you're wondering, well, that's great, Matt, but how do I learn how to design a chip? And will it make me a better person? Then the answer is to check out my Zero to ASIC course, where I've helped hundreds of people like you to design their own chips, and yes, you'll be the best person ever. Thanks so much for the tour today, Sebastian.
You're welcome. Thanks for coming to IHP.
I hope you enjoyed learning a bit more about how the microelectronics that power our everyday life are manufactured here at IHP. And if you want to learn how to make your own chips and even get them made, then check out my Zero to ASIC course and sign up for the newsletter. Thanks for watching.
Okay, so that's Matt Ben. No, that's Matt Ben. So he's the force behind Tiny Tape Out. And this was a tour of IHP's facility. So this is a fab in Germany, of course. We're using a fab called Skywater, 130 nanometer process. IHP's process is kind of similar. The exciting thing about Sky 130 is that they opened up the PDK, the process development kit that defines the technology so that everybody could work with it. And that enabled, everything that you're doing with Tiny Tape Out, really. IHP followed suit and opened up their PDK as well more recently. So I think there's active work going on, is my guess, enabling Tiny Tape Out to work with IHP's process as well. All right, so let's look at design teams. So various roles on a design team, right? When you're starting off a new project, that project is defined by the business leaders. They work with architects who define the design at a high level. The architects work with the logic designers who are responsible for implementing the RTL, right? So basically, the architect sits between the business leaders, helping to define what the project is, meeting business objectives, and connects that with the lower levels. So the logic designer is the verification team is responsible for verifying the functionality that's created by the logic designers. The implementation team is responsible for implementing the design that comes from the RTL. So they're direct consumers of the RTL. And after the RTL has been sort of signed off by the verification team that it's ready to go, and you want to push the button on the tens or hundreds of millions of dollars that it takes to fabricate the silicon, the design goes off to the fab. When it comes back, the post-silicon engineers are responsible for verifying the physical silicon. So obviously there's a close relationship between the verification engineers doing the pre-silicon verification, the post-silicon engineers doing the post-silicon verification, and all working with the logic designers. So let's look at these roles in a bit more detail. First, we'll look at the chip design process overall. So, essentially following what I just described, but focusing more on the evolution of the project versus the roles. So again, everything starts out with defining the requirements of the project. What is the project? And from the requirements, how are we achieving those objectives? So what's the specification of what we're implementing? What's the architecture that is going to enable us to implement silicon that will meet the requirements? From this specification of what it is we need to build, that feeds the verification plan, right? So how are we going to verify that this design is meeting all of these specifications? These specifications also deliver into the floor plan. So as you start to understand what exactly it is you're building, you can start to floor plan the chip, lay out what logic is going to be where, how much size are these different units going to take, what are the units, what's the routing between the units. This is mostly kind of spreadsheet work to make sure that the the architectural plan is implementable. You'll also have some early modeling for estimating the power to make sure you're meeting your power budget, and doing architectural models and performance models to make sure that, well, for one, at a high level, your architecture is functioning correctly, and also that it's performing to specifications. And of course, all of this work, you know, it's not just a forward flow through all of these steps. These steps are all learning experiences that feed back into the previous steps. So your performance model might tell you there's a performance issue, and that would feed back into the architectural spec. You might have difficult, you know, floor plan issues that require rethought. And even the requirements are not static. The ecosystem changes around us, the requirements change from above. So, you know, you're sort of starting out at a high level and working your way down to more detail. So more detail means floor plan becomes implementation, where you know, once you actually have RTL to model your hardware, you can actually run logic synthesis and place and route tools to understand your implementation in more detail. Also, as your RTL model is coming together, of course, also driven by the architectural spec, you work on your verification environment and connect that to the RTL to verify the functionality. All of this is the modeling that's done. You're also working with those models. So the performance and architectural models allow you to do performance modeling and verification work. The verification environment and the RTL enable you to do functional verification work. So writing test cases and running those test cases and debugging those failures, etc. So again, once essentially once you've checked off all of the items that you defined in the verification plan, and the verification team says, okay, we believe this is, you know, 99.9% likely to succeed, or whatever your sort of confidence targets are, you go ahead and tape out the chip, which means you provide the data that goes off to fabrication and becomes the silicon, and the silicon comes back, and you start the post-silicon work. Any broad questions? So just diving into each of these roles in a little bit more detail. One slide on each, well, one slide on most, and then we'll go more into verification. So the architect is defining the project. They're balancing the business needs with the feasibility of implementing this thing. Mostly they're working with slides, you know, high-level block diagrams, spreadsheets, this kind of thing. Not so much the tangible, simulatable models, although they might be working with some high-level models, performance models as well. Generally not hands-on with the RTL. The logic designer, basically, logic designer's role is simple. That's what you were in this course. Logic designer has one responsibility, and that's delivering RTL. But to do that, you're balancing, you know, all the trade-offs. You're balancing trade-offs for area, performance, power. People talked about this term PPA. It's power, performance, area. Those generally are the three main characteristics of the silicon that you tend to be focused on optimizing. Certainly not the only ones. So, you know, focused at the RTL at the logic level. Verification world is a bit more complex than the RTL world. Verification tends to deal with a myriad of languages, myriad different tools, environments, ways of approaching a problem. So in general terms, the verification engineer is creating the test bench. That's sort of everything surrounding the RTL. That includes transactors that are driving stimulus into the RTL. So the tests define what that stimulus needs to be in some way, right? For the CPUs that you guys designed, that would be a test program. the transactor is responsible for applying that test program to the model. So in the case of the CPU, that's pretty simple. That's basically an assembler. You get the code into the model, into the instruction memory. For most designs, there's a little bit more intelligence around taking that stimulus in some, higher level description and actually driving the physical pins of the design under test, the DUT, which would be your RTL model. And this happens at all levels, right? You have an environment like this at the unit level. Maybe your unit is your CPU core. You have an environment like this at the full chip, which might be a many core chip, and maybe you've got, like Apple's designs, the M series, M1, M2, etc. They have CPU compute engines, they have AI accelerators, they have GPUs all on the same chip, right? So you'd have a verification environment at that level as well. On the other side of the RTL model, you are checking the outputs to make sure they're correct. So you need to monitor the outputs. The monitor, is basically like in the opposite direction. It's taking the pin level details and up-leveling that in some fashion. Other tools connect, at the interpretation of the output signals. So models and checkers, coverage monitors looking at, generally looking at the internals as well of the design under test and making sure that the stimulus that you're providing is covering the situations that you intend to cover. You might have some visualization, you might have performance modeling that's kind of watching over the RTL to make sure that the RTL and the performance models, performance characteristics are in line with each other. And in addition to all this, so this would be dynamic verification or functional verification that's based on simulation. We also have formal verification, which is a more mathematical, proof-oriented verification to prove properties about the design. Prove them 100%, for all scenarios, not just for particular simulations with particular stimulus. The verification engineer is also perhaps responsible for completely, well, not completely, but a partially separate world that looks very similar, but is based on hardware emulation instead of simulation. So hardware emulation is using, generally this is FPGA-based platforms for modeling the behavior of the hardware. Basically, you're running your design in the FPGA instead of running it in simulation. So the RTL DUT, design under test, is synthesizable and therefore can be run on the FPGA hardware. The rest of these components may or may not be synthesizable, and if they're not synthesizable, they need to be run in software on a host platform. So these hardware emulators will have FPGAs for running the design under test. That'll be connected up with a host system that would run the transactors and monitors, etc. Obviously, the FPGA is executing behavior very quickly. Whatever you have running in software is going to run, by comparison, much slower. So the speed of these systems tends to be gated by the software components. So often these components need to be different for the hardware emulation platform than they do for simulation. There's a large push right now to make those two environments more compatible with each other. TL-Verilog actually potentially plays a very important role, since TL-Verilog is modeling things at a more abstract level. The modeling methodology of TL-Verilog is more appropriate for performance modeling than RTL would be. If you model these components, the transactor and the monitor, using transaction level Verilog, you're naturally synthesizable. So you can fit these components then on the FPGA as well, and thereby not limit the performance that you can get for hardware emulation. But especially since the simulation-based environments generally come together sooner. The hardware emulation often, although it shouldn't be, often is an afterthought. Often these components get developed in a way that's not friendly to emulation. So there may be some additional work to develop transactors that are appropriate in this environment. You know, you can afford to do a lot more with the transactors and the monitor in simulation, since your simulation speed is limited by the simulation of the RTL anyway. When you're doing hardware emulation, you're really trying to hit those deep simulation cases. So it might take days of simulation to get through just hardware reset alone on a full chip system. So you might use the hardware emulation platform to do the reset sequence. You might use it to do Linux boot, for example. And you can't afford to have the same level of software running in that ecosystem as you can pre-silicon when your simulation runs are shorter. Not pre-silicon, in simulation. So there might be considerable work to rework the nature of the transactors and the monitors. There'll be things that you would run when you're running simulation that you would disable for hardware emulation. Essentially, though, the nature of the modeling kind of fits this picture either way. And so the physical designer, and we're going to come back more to the verification role since it is so intricate. But the physical designer is fed the RTL. They run logic synthesis, place and route. Right? So logic synthesis is coming up with kind of the gate level model, and then place and route is placing the gates physically on the across the silicon area that's available and connecting up the gates. So the physical designer will be responsible for floor planning the different units, and then implementing, running the logic synthesis, place and route on these different units, getting the connectivity all correct, and coming up with the implementation of the design. And again, this is all iterative, right? So the logic designer is working on the RTL, the implementation team is running logic synthesis, place and route, they uncover timing issues, they uncover floor planning issues, they feed that information back to the RTL designer, and it's a lot of back and forth. After you tape this thing out, silicon comes back. Post-silicon engineer is responsible for verifying the silicon. So primarily, so post-silicon, we have platforms called testers. The testers, you drop the chip into the tester, you hook up all the ins and outs. The tester is going to drive what are called test vectors, which is just all the 1-0 patterns at the inputs, and check the 1s and 0s coming out at the outputs. Very simple in concept. Post-silicon, you're also going to test for reliability concerns, putting this chip under harsh conditions. You'll send it over to Los Alamos Labs, which is high elevation and tends to get a lot of radiation and activity, particle strikes coming from the atmosphere that can cause mischief on the physical silicon. And simulated harsh conditions in labs. They'll also test the power characteristics of the model. One of my brief roles was coming up with the power virus for one of the chips that we created. So the power virus is the test that will be run to stress the power as much as possible on the chip. So every chip that comes out of the factory is going to go through a standard litany of testing. The power virus is part of that. So they're also kind of in line with that, responsible for yield testing and binning. So one design, one chip is not necessarily one product, right? So for example, I worked on x86 CPUs, so maybe we have a generation of x86 CPU that's a 16-core design. We'll sell that as a 16-core high-end design. We'll also sell that as a 12-core design. And if we get a piece of silicon and we run that through manufacturing tests and we find that there's a bad core or two on it, we'll drop that into the 12-core bin and sell it at a cheaper price. And also the clock speed of the chips, right? So we'll crank up the clock on these parts and see where they fail and then back off a bit and bin it appropriately into a particular clock speed bin, right? So over the years, over the course of my career, the binning strategy has gone from no strategy, it's one chip, it's one product, to incredibly complex binning strategy that involves multiple people to sort the whole strategy out alone, and then, you know, more engineers to execute on that strategy post-silicon. Let's see. Of course, you know, their primary role is to, you know, early on, you get first silicon back. There are obviously going to be a lot of issues with that silicon. They're trying to bring it up. They're trying to get out of reset, get through the boot sequence, get through Linux boot, and get the parts stable so that we have some stable parts to do more tests on. And they're working with the pre-silicon team to debug issues that they find post-silicon, to, once they find issues post-silicon, to somehow recreate that in the pre-silicon world. And of course, the post-silicon engineer's job doesn't just start when the physical silicon comes back. There's a lot of preparation work to work with the pre-silicon team to make sure that all of the functionality that's going to be important for the post-silicon team to do their jobs actually gets into the silicon so that they have the visibility, right? I mean, it's a very fundamentally hard thing to debug a piece of silicon. It's a black box. It's very hard to see what's happening inside. You know, you've debugged in MakerChip where you have access to all the signal values. You can figure out what's going wrong. You've also worked with the design on the FPGA, right? Once it's on the FPGA and it's not behaving right, the bug that we had with the debalancing logic, for example, I mean, we're working with a very simple design, yet we had a bug that was difficult to debug. Very difficult when all you have is a black box that's, you're telling to add 1 and it's adding 6. What's wrong? How do you see that? You need to put hooks in the hardware so that you can inspect what's going on internally and figure these things out. That can be quite intricate and challenging, especially since you don't know what's wrong until it happens, and if you don't have the visibility at that point, you're kind of stuck, right? That's been a multi-million-dollar process wasted if you can't figure out what's wrong with the hardware. So, you know, as I said, all these different roles, the engineers are all working together. It's a highly collaborative process. At least it should be. If it's not, you'll never get silicon out the door. So how are these groups working together? You know, we have the lines between them kind of indicating where there's a strong connection. The logic, since the RTL is kind of the center of the universe defining the behavior of the silicon, tends to be a very central role communicating with pretty much everybody else. But so the logic designer is working with the architect to define the design that's being implemented, right? The architect is providing the PowerPoint level. The RTL engineer is implementing that in code. Logic designer is working very closely with the verification engineers to verify the functionality that they're working on, right? Defining the verification strategy and debugging failures when they pop up. Working very closely with the physical designer, right? When there are physical difficulties with the design that require rework at the register transfer level, that feeds back to the logic designer. And then when we actually do have silicon, right, the verification and logic designers especially are very involved in the process. I mean, many of the folks who are pre-silicon verification engineers and logic designers will then pick up responsibility post-silicon as well. And they're all working closely together to understand the failures that happen in production, take those failures, reproduce them in the pre-silicon environment so that they can be debugged And as I said, the pre-silicon, the post-silicon engineer is doing a lot of preparation, working with the logic designers to feed in these features, which would be referred to as design for debug and test, especially to make sure those features are in the RTL model. So verification engineers and post-silicon engineers are also working together closely on the environments to make sure they have a post-silicon environment in place for verifying the physical silicon and leveraging as much as possible from the pre-silicon work. So, test content that's written pre-silicon, we want that to be portable so that you can run that post-silicon as well. And that's especially where there's a lot of activity right now with a methodology, a tool, a language, I don't know, to support this called portable stimulus to write tests in a way that is portable to post-silicon. And of course, in addition to those roles, you've got managers, you've got folks that are focused on things like performance modeling and power modeling. You've got a team of folks probably focused on reliability and scalability, so making sure that the designs that are fabricated are as resilient as possible and scalable to large systems. You've got analog components on the chip as well, of course, and you've got a team responsible for the tools and methodologies that are used by the organization, so the internal EDA. So this slide is kind of illustrating that design is all about trade-offs. It's really more art than science. You're balancing a lot of conflicting needs and trying to come up with silicon that best balances all those needs. The boldest item here is schedule. That's always a strong message early, and it's an even stronger message late as the schedule starts to slip more and more. So, getting out the door, I mean, a lot of the benefit that we get from next generation silicon comes from the technology benefit, the scaling of the technology. So just getting something out the door on the new technology, you're getting a performance boost. So you want to get to that as quickly as possible. You get additional performance boost and functionality improvements, et cetera, from architectural change. But a lot of the benefit is just from getting the old design to work on a new technology and getting that out the door as quickly as you can. So schedule is always number one. I mean, I think every project I've been on, by the end of the project, we have a meeting and our leader stands up and says, top 3 priorities are schedule, schedule, and schedule. And, all these other things as well, right? Performance, power performance and area, PPA, right? Those are big. You want to find the right balance in those. And of course, you have different customers for your project, for the silicon, and you want to satisfy the needs of all those customers, which of course are not all the same, right? So obviously correctness is important, and it needs to work. So scalability was kind of making sure that you're covering a range of customers, from the small scale designs to the customers that are going to, build massive systems out of the chips. Serviceability, performance, of course, risk, scope, right? So as much functionality as possible to cover as many customers as possible, but then the more functionality you add, that takes away from other aspects of the design which affect your other customers. So again, it's all about balance. Reusability. This always, I don't know, was a point of contention for me. I always thought it was important to make sure that all the engineering work that we do for one project carries over to the next project and we can benefit from it. Organizationally, we tend to be designed for the project and all of our goals are about that project. But okay, any questions or thoughts? Yeah, so this slide is more of me rambling. I don't know, I probably shouldn't have put this in here, but I've got the stage, so I'll ramble about my hot issues. So I always felt that the design team should work in a bit more of a robust fashion, right? It tends to be the largest voices on the teams are the ones whose whatever their hot button item happens to be, we tend to, you know, kind of skew things toward the loud voices. So to me, it's kind of a simple framework here. The architects are defining very big picture, what's the project, right? There's some curve that's balancing all these myriad factors. The architect is putting us generally here on the curve, right? This is what we want to target. And then the logic designers are making these microscopic decisions day to day that move the dot small amounts, right? So at this scale where the logic designer is working, we're in a linear region. So to me, the role of the architect is to define where we are on the curve and define the linear trade-offs in this whole complex trade-off space, right? And once you have that linear equation that the architect could define, right, you can put it all in terms of dollars if you want to, right? What's the value of performance for this product? You've got some linear factor for the value of a delta performance or a delta power or a delta area. And you can put that all in a big linear equation. Once you have that equation, now you've got the framework to make the day-to-day decisions about, okay, if I make the cache twice as big, is it worthwhile or not, right? Let me find the sweet spot for the cache size. So it, you know, in my mind would take away a lot of the meetings and a lot of the back and forth. Verification, so essentially the whole design process is a process of going from some very high-level definition of what you're building to refining that down. So you go from, in our case with the CPU, an instruction set architecture that you need to implement, down to the register transfer level that's implementing that functionality. Maybe there's a model or two in between there as well. From there, it's tools doing the work to get, primarily tools, to get to schematic, and from there to layout. Each of these steps is, you know, in this case, to get down to the RTL, it's a manual step. Lower than that, it's tools. Regardless, something needs to be in place to verify the process, whether that process is tools or humans. Humans wrote the tools, right? The tools can be faulty. So functional verification and formal verification is all there to test this work. Since that's human work, that represents a lot of human effort to verify. Logic synthesis, we have, you can do formal verification or gate level simulation to verify that the schematic level, gate level design matches the register transfer level. Place and route, we have something called LVS, layout versus schematic, to verify. So this is basically two independent tools, you know, to cross-check each other. One doing the work, one making sure the work was correct. So I'll go in more on verification, since verification is a very important role that represents a lot of the work in the design process, and also we didn't focus on verification in the work that you did in the course. There's a document called the International, is that right? Yes, International Technology Roadmap for Semiconductors, ITRS. You know, it was a very broad effort to define where semiconductors are headed, identify crucial issues, help guide government decisions, things like that around the industry. So this document, I don't remember what year this was. This was, you know, several years back, but identified verification as a crisis area. And of course, it's only become more of a crisis since. Verification is hard, right? Like I said, logic design is just RTL. So you're right. And below the RTL, we have tools that help us verify that the work that we're doing is correct. But verifying the RTL requires many tools, many methodologies, and it's really difficult to know when you're actually done the work. One bug can result in a need to respin silicon, easily hundreds of thousands. That's a low ball, I think. And months of work, which could mean going out of business, right? It's a big deal. Bugs matter. Generally, today we see about 2 to 1 for verification engineers versus logic designers. The amount of code that verification engineers produce is probably 4 to 1 versus logic designers, right? Which kind of makes sense. Verification creates as much, as much as they can to provide stimulus to this model, whereas the RTL, you really want it to be carefully maintained and controlled, and you don't want, churn in the RTL is problematic. For verification, it's throwing as much as this thing as possible. In a sense, I mean, you want to do that in a thorough way where you can measure progress and so on. And after saying all this, there are very few colleges that offer courses in verification. I'm going to assume there's not a full course on verification at IIT Bhubaneswar, and that's certainly not unusual. The unusual is to have a course like that. Some of my colleagues that I've worked with for many years are actively driving verification curricula into universities. So the nature of bugs, right? Early on in the design cycle, the designs are not very mature, they're evolving. Bugs are easy to find, so you have a lot of bugs. They're not worth very much. As the design matures, there are fewer bugs out there. The bugs are harder to find. They're more complex in nature. They're also incredibly more costly, right? I mean, when you have a piece of silicon in a customer's hand and you stumble over the Intel floating point bug, that costs you big time. So it's just this kind of progression, somewhat exponential in nature, of the number of bugs versus the cost of the bugs. The more disciplined you are about verification, the more this bug curve looks like this bug curve, right? Where if you're focused early on robustness of your verification infrastructure, you're not spending as much time just trying to grab low-hanging fruit and identify bugs quickly. You're not going to catch the easy bugs so fast, but you're going to build a more robust environment, and over time you're going to start more reliably finding the bugs and have a more regular sort of tail. The solid line here is, that's more reality. This is more aspirational. A couple plots I pulled from Wilson Research Group, which does studies and surveys and so on in the industry. So I don't know exactly this kind of the range of ASICs that were covered here, but this is the data they collected over. I guess there's a 2-year cadence here on the data, so this is over the past 6 years or so. So percentage of projects that are successful on per silicon, and you see, a number of projects take 7 spins or more before the company goes under, I guess. These are the companies that were left around to talk about it in the Wilson report. This breaks down the nature of the bugs that cause respins to be necessary, right? So this is the far right tail of the bug plot. One of the interesting things to note here is that logical or functional bugs, well, first of all, if you look at all these bars, you'll note that they add to more than 100%. I believe what we're looking at here, I believe the bars will total the average number of respins, right, as a percentage. So if we're looking at an average number of respins of 2.1 out of this data, whatever it might be, the total here should be 210% on these bars. So logical or functional bugs is around 50%, right? I don't know what that is as a percentage of the total, but it's a fraction of the total. The rest of these, almost all of the rest of these, are analog in nature, physical in nature. So the point being that digital logic, functional bugs, is easier to verify pre-silicon than these physical and analog type of issues. I think there are 2 bars here maybe that are digital logic in nature, safety features, security features, and I think the rest are kind of analog-y. So clocking, tuning of analog circuits, crosstalk, so wires interfering with each other, signaling interfering. Power consumption issues, mixed signal interfaces, yield or reliability issues, so timing paths not meeting timing, firmware, software verification in all of this can be a significant effort on its own. I'm not really talking much about the software and co-simulation, co-verification of your software or firmware together with your hardware, but that's also a big topic. Yeah, so we've got timing paths that are too slow and timing paths that are too fast. Both can be problematic. IR drops, again, physical, very physical in nature. Safety and security, you'll notice just sort of popped up on the radar for the last survey. Safety and security are becoming increasingly important. Governments across the globe are very focused on security. So any thoughts or observations about the data? Bugs happen all the time. It's a reality. So just some data on Intel 8th generation, 9th generation, 137 errata, since fabrication of the silicon. So mostly these are things that, there's some sort of workaround for in software, or they only relate to certain customers, and we're still able to produce the silicon and ship it off. But yeah, just to make the point that silicon does not come out perfect. A look at verification languages. So you can use VHDL or Verilog for your verification environment. I don't know why Verilog is so much bigger than, System Verilog is bigger. System Verilog, the delta of System Verilog from Verilog is mostly around verification functionality, features that, UVM you may have heard of is a library built on the System Verilog features for doing verification. Vera is a language that, you can see didn't get huge traction for doing verification. Many of my former colleagues, some of my former colleagues were off in that world a bit. System C is C-based modeling of high-level behavior, and you can use that for verification. SpecMan E also, some of my former colleagues worked on SpecMan E, another language for doing verification. C++, actually Vera, I'm trying to remember now if that was incorporated into Verilog in some form, but I forget the details. C and C++, when I started my career, most verification modeling was done in C++. And then System Verilog came along and took the lion's share of that. And these other ones, SpecMan E, Vera popped up, and then kind of never took off in full. PSS is the portable stimulus standard that I was mentioning. And I think the most interesting one here is this bar, which is Python. So what is it, CocoaTB, I guess. Open source, right? All the rest of these are commercially driven. this is the impact open source is having, right? It was 0 in the last 2 surveys, and now it's a substantial bar, right? So the trend line here is pretty astronomical. Hard to project from one data point, but I think it's telling. So a closer look at pre-silicon verification, right? We're starting off with the functional specs. We write a bunch of verification test plans. As I said, you're going to have unit level models, many of them. You're going to have a full chip model, a system level model. You're going to have a model for emulation. You might have models in between the unit level and the full chip level. So all of these are going to have verification plans. So these are the models. This is the work. You're going to be using the verification plans to, pound through all of the items in the plan and make sure you've got tests that achieve the desired coverage goals. So the test plans are going to incorporate, a specification of what all the coverage is that each category of testing is trying to hit. And then the coverage monitors are making sure that you hit those cases. And that's giving you a level of confidence that you're, kind of exercising the logic, all the corners of the logic as best you can. Yeah, of course, there's the actual debug work, right? So you create these models in order to do debug. You're debugging not just the DUT, but also the environments themselves to stabilize all the modeling so that you can run all the testing. Once all of your test plans are complete, and you feel you have adequate coverage, and everything is signed off on all levels, you'll tape out the design. So drilling more into the nature of especially the checking environments. So this drawing illustrates what would be known as a shadow model. So this is kind of the most simplistic view of creating modeling and checking for a design under test. So the shadow model would be a model that's pin accurate with the inputs and the outputs. So you drive your stimulus to your RTL, you drive your stimulus to your shadow model, you check the outputs of the shadow model versus the RTL and make sure they match. Okay. What tends to happen when you take this approach is that the gory details of the RTL tend to get exposed to the extent that the shadow model has to pretty closely match what the RTL is doing. You really get value when you can abstract things. So shadow model tends to force you into kind of a low level of verification. So what you can do to improve that is build models. So first of all, you stick a monitor on the RTL that's up-leveling the interpretation of the pins a little bit. So you're not specifically checking, maybe, well, I don't know, CPUs are not a great example here, but anyway, you're not specifically checking pin accuracy, but your monitor is interpreting those pins at a higher level of abstraction so that your reference model doesn't have to be, sort of incorporate that. By breaking off that function as a separate thing, you can share that work of abstracting the behavior for other models that are overseeing the behavior. Your reference model then doesn't have to know the individual pin level, and also your monitor can tell your checker, okay, this is what the RTL did. Your checker can tell the reference model, and that might impact the modeling, right? So for example, in your CPU, what's a good example? So we didn't do a branch predictor, but if we did do a branch predictor, it would be predicting take it or not take it. It doesn't matter functionally. It shouldn't matter whether it was taken or not. The CPU should function correctly. It's a performance feature. So it should be fine for either choice from a functional correctness perspective, but maybe the reference model has an easier time doing its job if it knows the choice that the RTL made. So as long as you're careful about it, it's okay to feedback that sort of information from the RTL to update your reference model and simplify things potentially. So you might have a little bit of connection in this direction as well. So yeah, so basically by up-leveling things, so for example, also you don't care from a functional correctness perspective when you're retiring instructions, you just care that they retire, right? So when the CPU retires an instruction, you'll check that it was correct. A shadow model would have to model the cycle level behavior and know when is the instruction going to retire, what's the exact cycle. In this picture, the reference model doesn't have to be cycle accurate. It just has to know this is the instruction that ought to retire next, and when it does, this is how it should be characterized. And the monitor can say, hey, we retired an instruction, and at that time you check it. Right. And this, I guess this is what I was saying earlier, is it's sometimes okay to look at the internals, right? So this would be representing that you're looking inside to see, was the branch predicted taken or not? And you might use that to update the way you model the behavior in the reference model. You have to be careful about this, of course. You should only be looking at internals for decisions that don't affect the functionality of the design, such as a branch predictor. Just to show kind of a common technique with these reference models, we'll stay in the context of a CPU, right? This RTL DUT might be, let's say, the guts of the CPU core, not including the instruction memory, so it's seeing instructions coming from the instruction memory. The reference model would look over those instructions and say, okay, I got this instruction, let's remember it. It's going to come out sometime later. When it comes out, we'll check everything off. So it's very common to use what would be referred to as a scoreboard to hold on to that in the case of a CPU instruction. So it's basically the scoreboard is watching things go in and then checking them when they come out. So you store away everything that came in, all the characterization of what that thing was. And then when you see it pop out, you check it off, remove it from the scoreboard. Assertions are, very low-level checks that might be internal in your design, right? A lot of our verification is focused on treating something, for the most part, as a black box. So you don't care how it's getting done, what's happening internally. You just want to make sure that the behavior that you're seeing from the outside is right. Assertions, they can be internal. You sprinkle them everywhere. Assertions are not your level of completeness for verification. Assertions are identifying bugs closest to the source as possible. They're capturing design intent. So, we've looked at muxes a lot, right? If you have a mux where the selects should be mutually exclusive, you might write an assertion that says, these signals that are controlling the mux select should be mutually exclusive. Mutually exclusive meaning at most one of them should assert in any given cycle. So assertions might also have a time aspect to them, right? For every request that we see, there should be a corresponding response within X number of cycles, right? Is maybe an example of a temporal assertion. Mostly the assertions, at least ideally, are written by the designers, capturing the design intent. So as you're writing your RTL model, this is what you have in mind. If there's a property that you can express as an assertion, that helps. You'd be surprised how many situations like this, you sort of think, okay, well, these are mutually exclusive. That's guaranteed by the logic, but something's going to happen somewhere along the way that breaks that. And if your error message is these signals are mutually exclusive versus the value in this register is wrong, right? It's a lot easier to debug. Just looking at an example at a code level. So this is system Verilog assertions, this SVA. So this originated as its own language and then was incorporated into the system Verilog standard. That's kind of the nature of the system Verilog standard. It's pretty much a vacuum for and an approval process. Kind of all these different technologies that have evolved from different places have gone through IEEE for ratification and been incorporated into system Verilog. So when you're defining an assertion, you first define a property. So here we've got a property that says signal ready has gone high within 5 clocks after a start was asserted. I'm not going to explain the syntax here, but that's what this says. Once you have the property, then you apply that property as an assertion. You assert that that property holds. So if the property does not hold, report an error. Anybody wondering why verification engineers exist? Why can't the logic designers just get it right? Why don't the logic designers verify their own designs? We don't write software and expect somebody else to verify our software, usually, although large teams will do that. You know, you do have QA teams and whatnot. But it's much more the expectation in the hardware world that the verification work is done separately. So there's a couple reasons for this. One of the main ones is the second set of eyes, right? Everyone has biases. Everyone overlooks things. I do it all the time. If you have somebody completely independent from you looking over your shoulder, their biases are different. They're likely to, you know, catch things that you might miss. Also, the nature of the work is very different, right? A logic designer tends to be focused on the common case, right? The logic designer cares about performance. They care about their implementation team as well as the functional correctness, right? Functional correctness is one of the many things in this earlier picture. And it's not even a huge, you know, it's a big one, but it's not a huge one. Logic designers worried about all these things. The verification engineer is concerned about correctness. Full stop, I guess. So, you know, it's good to have a team of engineers with that specific focus since it is important. Yeah, so it's a form of specialization and division of work, right? Do work in parallel. You specialize. The skill set required in verification is very different from the skill set required in logic design. Logic designer is responsible for RTL, thinking about hardware. Verification engineer is very savvy about software worlds, ecosystems, languages. You know, it's just a very different discipline. So yeah, this last very likely the logic designer is bringing up their design to a certain level of stability, but then the remainder of the work is picked up by the verification engineers. So the verification engineers are focused on not just the act of verifying, but creating the whole environment that enables that. Let's drill a little bit into tests. So the transactor, of course, is driving the tests into the DUT. The tests, we have, you know, different types of tests that would drive that DUT. So we have a focus test. In the case of a CPU, would be a program, right? It's doing one specific thing, trying to exercise very specific scenarios. We have random testing and varying levels of randomness in the testing, right? So the random testing, of course, is trying to give us a smattering of activity in the chip. where the focus tests may be drilling down into a very specific gnarly corner and trying to exercise something that if you just throw random stimulus at a design, you're unlikely to hit. Also, the focus tests tend to be easier to write, so you might do a lot of that early on for the path clearing kind of activities to make sure things are generally healthy enough to apply the random stimulus to, right? Focus testing, when something goes wrong, it's easier to understand what went wrong because the test is focused. You kind of know what it's trying to do, whereas the random test, you have to figure out what it actually did to a greater degree. We also have regression testing, right? And this is our way of making sure we don't go backwards. So as much as possible, as you're developing tests, you try to enable those tests as regression tests, meaning every time you make a change to the model, the regression tests will be run against that change and make sure they're still passing. So it's our way of making sure that we don't step backward. Anything that's in the regression test, that's a gating function for changes getting into the model, so they prevent bugs from getting into the design. Obviously, you want to balance the sort of the magnitude of regression tests versus the quality of the tests. You don't want regression to take 3 days to run. That's going to slow down progress on getting changes in, but you also want them to get good enough coverage that you don't have bugs creeping into your design that was once stable. Functional coverage. So we want to make sure, and I think we break at 4:15, right, Srinivas? 4 o'clock is our break. So functional coverage. So this is the kind of thing that would go into the test plan, right? So this is a coverage matrix showing that we want to make sure we're hitting various scenarios in the design. So just as an example, we define various events of interest, coverage points, and a sort of typical approach is to do a cross product. So you might have some interesting set of events, like here we've got a misaligned address, an unknown address, a page miss. So this would be some sort of memory controller logic. We want to make sure these events are happening with different scenarios of the memory access. I'll just wrap up this slide. So here we're looking at, I've labeled this load to use latency, right? So we're requesting a load from memory, for example. And a load to use would be the load instruction itself, which returns data, and then the instruction after it that consumes that register. So a load to use latency of 1 might be a load instruction followed immediately by an instruction that consumes that data from the load. Latency of 2 or 3 would be instructions after that. So, maybe we want to detect all these sort of exception conditions that relate to memory with different load to use latency. We create this coverage matrix. Then we run simulations and collect the coverage data, which might look something like this. So very often we have this unknown address with a load to use latency of 1, but we never do a misaligned address with that latency. And that guides our test development. So we can try to tune either the focus test or the random, the knobs on the random test generation, etc., to make sure we're getting good coverage across the board. Okay, so the test plan would just be full of these coverage matrices. You could imagine a 3D matrix. I don't know, maybe it's the limitation of human thought. We tend to do these two-dimensional matrices. And you can do one-dimensional matrices, of course, as well, just to make sure you're getting these individual events. So I think with that, we'll take a break. So we'll be back in 15 minutes at 4:15. All right, so let's jump back in. So basically the plan for the rest of the day is to continue through the lecture content. We probably will get through the lecture content today, and that'll wrap up kind of the body of the course. Tomorrow we'll jump into final projects, so I have some slides tomorrow morning to go through to introduce you to the projects, to give you some ideas for projects. You'll do some brainstorming about what you want to do for your project and define your goals, and then, you know, start off on projects. I think so. Tomorrow afternoon, it looks like I'm going to jump out after lunch. We kind of have a choice here, I guess. Dr. Bopu has some content that he could go through about FPGAs, the internals of FPGAs, the tools that are involved in FPGAs. So I don't know if you want to say something as well, but you could go through that content or continue to focus on your projects in the afternoon while I'm gone. I'm also, so I will be here through Thursday, and then Friday my flight leaves in the morning. So Friday also, you guys have class project time to kind of wrap things up as best you can while I'm flying. So think about it. We'll make a decision, you know, tomorrow about what we'll do tomorrow afternoon and what we'll do Friday. But if there are things that you're hoping to go into more, we can do that. AI showed up in the title of the talk. I didn't get any specific slides together for AI, but we can have an open conversation about AI in the silicon industry. We'll fit that in somewhere as well. Okay. So we were talking about coverage. So we talked about creating these cross products and filling them in. These would be, these cross products are defined by the engineers. There are other types of coverage that are automated. So that you sort of get them for free for whatever they're worth. So there are various types of code coverage. So you might hear terms like line coverage, statement coverage, expression coverage, branch coverage, condition coverage. These are various metrics of that just analyze your code and make sure every line or expression or statement, what have you, is executed. Branch coverage would be every control flow expression in your RTL code, right? Your hardware description language code is executed. Condition be a similar term. These don't really apply to TL-Verilog because we don't tend to write our code to use these sort of conditional sequential representation, but nonetheless, these are all terms you might hear, and they're all just measures of the code execution coverage. How many times did I execute this statement in my code, my RTL? Logic coverage is more analysis of the logic that is implied by your code and how often that logic is exercised. So it might be things like toggle coverage to make sure every Boolean signal in your model is toggling between 1 and 0, or expression coverage to, you know, if your expression is under conditions, make sure the expression is evaluated, or different cases within that expression are evaluated. Path coverage, so some of these terms are sort of dependent on the modeling methodology. Finite state machines are very common to model in RTL. I say that, and I've like never written a state machine in my entire career in RTL, but you write them a lot in school. So a state machine is, you know, I'm in my ready state, I get some external stimulus, I move to valid, so on. So making sure you're hopping through all the states, making sure you're hopping through all the paths from one state to another, you can automate that. And assertion coverage, so in addition to expressing logic, your code is expressing assertions, which we just mentioned. You can make sure that the assertions or the properties that you're defining for your assertions, the temporal logic that you're expressing in those is exercising kind of all the temporal steps. The assertions might be asserting state transitions, so make sure those transitions are happening, things like that. Okay. So formal verification. So formal verification, unlike functional verification or dynamic verification, same term, two terms for the same thing. Formal verification is sort of proving without a doubt that properties that you have defined on your model hold. There are two main categories of formal verification. There's model checking. In model checking, you explore for some number of cycles the entire state space that can be reached by, on that hardware. So basically, for any possible inputs to your hardware, what possible states can I reach? This kind of explodes as you go forward. The number of states that you can possibly reach gets exponentially large to a point, and then you kind of reach all possible explorable states and it tapers off. Formal verification, whether it's model checking or theorem proving, tends to work to a certain scale and then explode. I mean, sort of the nature of state spaces is the more bits of state your model has, the more states you can enter, and it's explosive, right? If you have one more bit, you have 2x the number of states. So exponentially, your model grows in complexity and the formal verification effort grows. So you tend to sort of reach a certain scale and then formal verification becomes infeasible. So theorem proving, unlike model checking, which is bound to a certain number of cycles, theorem proving is ensuring properties for all of time. A common approach with theorem proving is induction. So, for example, I can prove a property for a structure that contains one entry. Okay, my property will be much simpler to prove with one entry than with 1,000 entries. Prove that it's true for one entry, and then also prove that if it's true for n entries, it's true for n plus 1 entries. So proving that delta between n and n plus 1 can be a fairly simple proof. If you can prove that it works for 1, and you can prove that if it works for n, it works for n plus 1, then you've proven that it works for all possible sizes of a structure. Right, so these are basically defining mathematical, if you want to say math, I don't know if that's the right term, but lack of a better term, mathematical proofs on the hardware model that you've created that properties must hold. And you can also imply induction not just for sizes of structures, but depth of simulation, right? If this you can prove that a property holds for the first cycle of simulation, and if you can prove that if it holds for the first cycle of simulation, or sorry, if it holds at a particular cycle of simulation, that it must hold for the next cycle. I shouldn't say simulation. If it holds after so many cycles, after n cycles, then it must hold for n plus 1. If you can prove that, and you prove that it holds for the first cycle, then it is proven for all of time, right? So I would say generally model checking tends to be the one that gets the most focus in formal verification. Theorem proving tends to be a little more manual to come up with the proof yourself, as opposed to model checking is largely automated by the tools. Of course, theorem proving is more robust in that it's proving the property for all of time, not for a limited number of cycles. One use of formal verification is equivalence checking. where you've got two different models that should be functionally identical, and you want to prove that. So it could be that A is an original version of your hardware description model, and you make a change to that that should not affect behavior. So that's model B. So you have, model A is version 1, model B is version 2. You want to know that you haven't broken anything when you made the change. So you can connect up those models, basically driving the same input to both and putting a comparison on the output to make sure the outputs match. Your property is this, this matching check must hold for all of time, and then you apply, say, model checking to make sure that's true. This circuit is known as a miter circuit. A and B also might be, A might be the RTL for your design, and B might be the gate level design after running logic synthesis. And you'd be using this approach to verify that logic synthesis didn't break anything, verifying the tool in this case. So other than equivalence checking, right, it's important to note that for formal verification, just as for dynamic simulation verification, we need test benches. You need to specify the constraints on the inputs, right, so that the test benches are different in nature. But you need to constrain the inputs to legal inputs, whatever the external logic is to the unit under test. There's bound to be assumptions, right? Maybe this input vector is a one-hot vector. If you're not constraining the formal tools, they're going to come up with a multi-hot vector that violates the properties that you're trying to verify. So you need to define the input constraints as properties. In order to define those properties, if those properties are complex, you might need to actually create some logic, which you'd refer to as a transactor in this scenario as well, that provides those constraints, right? So maybe, I don't know, maybe you have two input values that are dependent on each other, right? One is this one-hot vector that selects something, and the other should come along 3 cycles later and align with that one way or another. You might need to define some logic at the input that's generating those, in sort of a controlled way to ensure the property that you need on the input. So again, the nature of these transactors is it's different from what you might create for for functional verification. But it's kind of an easy oversight to make, that you think, okay, this is all formal, it's tools doing the work, I don't need a test bench, I just apply the tools. There is work to sort of create the test bench that supports these. And then similarly on the output side, it might be essentially necessary to create a reference model to define the assertions that you're looking for at the output, where the reference model is modeling the behavior that you expect, so that you have a reference to compare against to create the properties that you're checking at the output, right? So depending on the nature of the model, there can certainly be a fair amount of work on the verification modeling around the formal verification effort. Basically just to say it's not free. Okay, so you may have noticed a couple slides back was sort of the point where I lost energy and the slides became very wordy and less pictures. So I've got a number of slides about post-silicon verification that are very wordy. So the nature of post-silicon work, right? There's, as I said, no visibility into the silicon unless you explicitly create that visibility. So you need to add features that will capture internal state, enable you to reproduce bugs in simulation where you can figure out what's going on. Repeatability in post-silicon verification is very important. You're running on, in a post-silicon system and something goes wrong, what do you do? You can't do much unless you can reproduce the issue, right? And that can be very difficult, made difficult by a number of things. First of all, your design is likely to have many different clocks. The clocks might be synchronous with each other or asynchronous. Where they're asynchronous, this is problematic for reproducibility. There's no way to reproduce exactly the same behavior if the clocks are not forced into alignment. So, the asynchronous nature of those domains is certainly a consideration for the post-silicon work. Physical issues and manufacturing defects, right? These are by nature hard to predict. If your silicon is just not reliable, you have a bit of memory that you can't trust to actually hold a one. Sometimes it might work, sometimes it might not. It's hard to reproduce. External inputs, right? You have to consider how are you going to reproduce exactly the same inputs if those are, if those affect the nature of the bug that popped up. So those could be things like the external disk or a mouse click even, right? Any asynchronous process. So in this context, asynchronous doesn't necessarily mean there's no clock, but it means that it's somehow free running or difficult to control. So I'll use a DRAM, for example. DRAM has a requirement, so DRAM being a external memory. So DRAM has this requirement that you periodically send a refresh, and the refresh is needed to make sure you're not losing data. So the refresh is kind of, boosting the stability of the data in the memory. This just has to periodically, every, I don't know what the numbers are, but every million cycles you have to send a refresh to the memory. So if your tests, if you happen to hit a bug, and that bug is sensitive to the timing of the activity in the memory, if you're going to reliably reproduce that bug, you have to reproduce exactly the same synchronization of the memory refreshes, right? So philosophically, those memory refreshes, that's a background process that just, you have some logic that sits off to the side that generates these refreshes, and the refreshes have to inject into the memory. But to inject them into the memory, they affect the mainline logic, and they affect the timing. So processes like this can make it difficult to reproduce bugs post-silicon. Even though the impact, is conceptually very minimal, it's very rare we do a refresh, who cares that we're losing a cycle, but it affects our ability to reproduce things. In order to enable post-silicon work, there should be a very clear focus pre-silicon on making sure that the functionality of your hardware is stable enough to at least get out of the boot sequence. Sort of secondarily to make sure, well, first that you can reset the silicon reliably, then that you can boot the silicon reliably, whatever the boot process is. If you're talking about a CPU, it's really good if you can get Linux up and running. So you want to put extra focus on these sort of sequences that get you up and running to make sure you can get to the point where you have more ability to do the post-silicon verification work. You also, bugs that are found post-silicon, right? The fix to them means you fix your model and you do another tape out. It's obviously very expensive. So we need to do some things to mitigate the risk that we have to do another respin to fix post-silicon issues. A couple things that we can do for that. So, first of all, if we do really have a post-silicon issue that's blocking, you can go in and do a very focused fix to a individual piece of silicon using a technology called focused ion beam, or FIB, and go in and actually change the physical hardware. Okay, expensive equipment to do this, it's an expensive process, and it's one piece of silicon at a time. But if you really do have silicon in production, or not in production, if you've manufactured silicon and you're trying to do the post-silicon verification work and your part is dead, yeah, you're going to fib it instead of doing a respin on the part so that you can make forward progress on at least a handful of parts. So we'll talk about other mitigation strategies for post-silicon in subsequent slides. So all of the work that you do kind of pre-silicon to prepare for the work that's going to be required post-silicon is called design for something. Not exclusively for the post-silicon, but all these sort of ancillary features that need to exist in the hardware that aren't the main functionality of the hardware, but they're important to be able to get reliable hardware into customers' hands. Designed for something, right? So test is sort of the testing the physical manufacturing quality of the parts. Debug is doing the post-silicon debug work to ensure functional correctness of your physical silicon. Design for reliability, designing hardware to ensure that it's resilient to harsh environments, that it is going to stand the test of time, right? It's not going to age out and start to cause errors after 10 years in the field. Design for yield, to make sure as much of your silicon as possible is quality silicon. Design for manufacturing, design for security, scalability, yeah. They're similar. So I will say more about reliability, not these. So design for yield, for example, a design for yield consideration might be so I was thinking the CPU example that I mentioned before, right? You've got multiple cores and you want to design them in such a way that if there's a failure in one of the cores, that you can configure the system to disable that core. That would be designing for yield. Design for manufacturing, obviously, I'm actually going to struggle to come up with design for manufacturing example. But yeah, I think they are similar. So a little bit of focus on the top three that were in bold. So design for debug first. This is your insurance against bugs in post-silicon. And obviously this is all functionality that you need or you want to get in the silicon to help with the post-silicon debug effort, but it's not part of your product, really. So you're trading off debug visibility and repeatability with the area that logic consumes. It's generally not really a power concern because it would be disabled in production, but with also the pre-silicon design effort and cost, of course. Ideally, what you want is a system where, and I can thank my colleague for this list. I stole his slides, Scott Taylor. But you want a system where you can predict that a bug is about to happen, say 100 million cycles before it manifests, capture every node on the chip for all of time until the point of the failure, and be able to explore that data at our leisure, right? Or you want to be able to capture enough that you can reproduce that behavior in simulation. Obviously, it's kind of hard to predict the future. If we could do that, we wouldn't have designed the bug in the first place. So how do we get enough visibility? One approach is scan. So scan, and this is where my laziness to draw diagrams is going to hurt. But scan creates a chain through all of your flip-flops by which you can shift out all of the data stored in those flip-flops, right? So if we do full scan, that means every flip-flop is part of a scan chain. Then we can run run the CPU, freeze the CPU, run JTAG. I don't know, the acronym is named after the group that defined the standard, not what the standard is actually for, but this is a standard for defining these debug ports to be able to read out all the values on these scan chains from the flip-flops. So you're running, you halt the design, you shift out all the data from the flip-flops, and you've captured the complete state of the machine. You might also need to capture inputs if they're not themselves driven by flip-flops. Doing this can have like 5 to 15% area impact on your whole design. This may not be acceptable for your project, right? So you may not be able to do full scan. There's a distinction between destructive scan and non-destructive. Non-destructive means you can read out the values and then continue execution. Destructive would be the values are actually shifted out and lost as you shift them out. Typically, we're doing non-destructive. So with non-destructive scan, you can actually single-step the machine and capture all of its state for every cycle. So also, if you capture the entire state of the machine, you may be able to take that state, load it into a pre-silicon environment, and do simulation at that point. So scan is great if you can afford the area impact. If you can't, things get a lot more difficult. So as I said, you might also need to capture inputs if they're not driven by flops that are scanned. All these things that we talked about reliability, if you're stopping execution, but there are other things that happen asynchronous to the logic that you froze, you're impacting the timing of your simulation, so you impact repeatability. Yeah, again, asynchronous clock domains. The capture time for these can actually get significant depending how you design it, right? Because these scan chains are covering a large number of flops, and it's one cycle per flip-flop. The actual act of reading these values out, especially if you're doing the single-step kind of thing, can get significant. And then once you have all that data, it's a lot of data to process, so the tools that are processing that data could be slow as well if you're just sort of blasting a whole bunch of data. So if you can't do full scan, one approach is to do trace capture. A design like a CPU has memory, it has caches. These are storage structures. So if it's hard to get this massive amount of data out of your chip, basically with debug, you've got all this information on the chip that you want to capture, but you have a very small funnel to get that information off chip. So you can take advantage of the fact that you have memories on chip and capture some of this trace information on the chip. So first with for designing for debug, you want to identify important states on the machine that can give you a good understanding of what's happening inside the machine. Once you've identified those, you need to be able to capture that information somewhere. So trace capture, you would funnel this information into a memory or a cache or some structure that's already there and use that structure to store it. and you can store it over some window of time, freeze the machine, and by some means read out the data in that memory or that cache structure. This allows you to sort of leave the machine running while you're capturing the snapshot, which, again, depending on these asynchronous external properties, might give you a better understanding of a real situation where you actually can catch the bug. So what should you be capturing? You want to identify key signals, for your CPU. You might want to capture the stream of instructions that's coming out of the instruction memory, or the stream of instructions that's retiring. What's the history of the program counter? That will tell you the nature of the program execution, things like that. You want to be able to, there's going to be more key signals than you're able to capture. So you want to be able to funnel these in a configurable way, right? If I'm trying to track something down that has to do with memory, I want to capture the key signals that relate to memory. So I want to configure my debug to capture those signals and dump them into my trace capture buffer or whatever that is, my cache region or something. So, generally the nature of these designed for debugs is you've got a whole bunch of state in the design that you want to be able to capture. You've got this network that's funneling all that data and a bunch of configuration that's allowing you to select amongst all this different data to funnel it down to some set of data that you can actually capture cycle by cycle. If you can repeat the behavior in a cycle accurate way, you can configure the design to capture a certain subset of data, dump that, repeat the exercise, capture some other subset of data, collect all the data up, glue it all together, and get all of the signals that you are funneling into your debug logic. That is only if you can do this repeatably, right? It's also important to kind of capture boundaries, all the input data going into a block of logic, so that you can reapply those inputs, right? So if you can capture all the state of some unit of logic, some boundary of logic, and you can capture the input values going into it over time, you can set up the initial state and reapply all the inputs and regenerate that in simulation. Another aspect of this that's important is figuring out the triggers that you can use to initiate trace capture, for example, right? So triggers are kind of similar in that you don't know what bugs are going to pop up post-silicon. This is all guesswork. So there are various conditions that may be relevant to the bug, right? Cache miss, or I don't know, a fault condition, or access to some particular memory address that you can set up, right? So if you find that there's a bug that seems to relate to addresses that are on a 4K boundary, for example, you'd like to be able to configure your debug logic to be able to trigger when it accesses a 4K boundary, right? So you build this network that is capable of, again, funneling in a bunch of potential triggers and then narrowing down on the ones that you think that matters. You're debugging a particular issue that relates to memory. You go in and you configure the triggers to be based on some memory event, and then you use that to capture. You get your data, whatever you can manage to capture, use that to narrow in on the bug a little bit more, refine the triggers to try to, catch something else. So for example, in a CPU, right, maybe you want to trigger when you fetch the instruction at a particular address. So you want to be able to set up your trigger for that. for the nth time, right? After loading an address from some other address for the nth time, that resulted in a second level cache miss, right? You want to be able to configure all these things. So the last bullet here, it's important to note that, you know, earlier I said you want to be able to trigger in order to capture an entire window of time so that you're capturing all the data that relates to the bug. You can play this little trick that just always capture and use the trigger to stop capture, and then you've got the history, whatever history you were able to hold in your buffers. So you don't necessarily need to predict the future to be able to trigger and capture. You just enable the capture and trigger the stop of what you're capturing. So all of this, I guess before I move on, is basically to, I don't expect you to walk away with all the details of how you would design an intricate design for debug environment, but I do want you to walk away with the impression that this is crazy hard. So that, you know, the examples that you're doing in classroom, in academia, building a CPU core, you're not considering all this design for debug. We didn't talk about design for debug when you built your RISC-V cores. All this kind of stuff has to be a consideration when you're doing real-world silicon. So D-features are also important. When you have a bug in post-silicon, you don't want it to cost you millions of dollars. You'd like to still be able to use the silicon that you created. Mostly pre-silicon, you've verified the model to a certain level of stability. Mostly the bugs that you're going to run into post-silicon are in these gnarly corners. They might relate to some really bizarre configuration of the core. Often they're with features that are not sort of mainstream important for all customers. So they may, in particular, they might be performance features. Performance feature you can turn off and still function correctly. You just take a performance hit. So things like that you want to provide D-features on. So when you're designing your logic, like we designed the register file bypass, right? Maybe we want a D-feature. Well, let's take, so originally we did our core so that it would issue an instruction every 3 cycles. And then we sped that up so we could issue an instruction every cycle. We might want a D-feature in our core that reverts us to that every 3rd cycle behavior. So we might want to keep that valid logic, that's the 3-cycle cadence, and have a configuration which would be controlled by a control status register that says, I want to revert to the every 3rd cycle valid behavior. And then if we have a bug post-silicon, you know, that's probably too much of a performance impact to actually ship that to a customer, but at least we can de-feature that so that our core is functioning correctly. And then we can get deeper into simulation. Maybe that enables us to boot Linux where we couldn't boot Linux before. So things like that you want to consider upfront when you're designing your silicon so that you have the ability to disable these sort of auxiliary features and nice to haves, right? Many of the features might be particular to certain customers, right? You don't want them to get in the way of the functionality for other customers, so just be mindful of how you add those. So design for reliability. This is basically about particle strikes from space. They're real. An alpha particle, which doesn't matter much to our bodies, matters a lot to silicon when you're talking about these microscopic, 2 nanometer sorts of scales, right? So these particles, neutrons, cosmic rays, don't ask me what all this means. I just know that it can hit your chip and it can flip bits. So they cause mischief. The smaller the feature sizes get for our silicon, the more likely it is that one of these particle strikes flips not just 1 bit, but multiple bits. So, and these events are frequent enough that if we did not protect against them, our silicon would not be reliable enough to ship to customers. So memories in particular, right? Memories account for a fairly large surface area on our die. The memories, the circuits are very compact. They're very susceptible to these particle strikes. If one of the bits flips in memory, you're almost, well, I won't say guaranteed. It depends on the software, but that's a visible impact to the silicon, to the program, potentially visible impact. If you flip a random bit in random logic, sometimes it manifests downstream in downstream logic. Sometimes it just sort of fades away depending on the nature of the logic. But point here is memories are particularly susceptible. They're also particularly regular, so it's easier to come up with ways of protecting the memory structures. So the approach we use with the memories is generally error detection and correction mechanisms, right? So there are various schemes to be able to detect errors in the memory and schemes to correct memory errors in the memory. Not just memory, but we'll start there. So the simplest of which would be parity. Who knows parity? Okay, so parity is simply the XOR of a bunch of data bits. Okay, so you XOR the bits, you store that value along with the bits themselves, and if a bit flips, and you recompute the parity, and it mismatches, you know something went wrong. You know a bit flipped. If two bits flip, parity still matches, you don't know any better. Okay, so that would be single bit detection, no correction. Well, yeah. You can do better than that, right? So there are more sophisticated schemes called error correction codes. There's a whole math behind it. Instead of keeping just that one parity bit, you do a various set of XOR-based functions to keep a bunch of bits, and those bits may have better protection properties. You might be able to actually not only detect an error, but correct an error. If this bit flips, you can figure out which bit flipped, you can flip it back. So you might have an ECC scheme that is, you know, triple bit detect, double bit correct, or triple bit detect, single bit correct, something like that. So you apply these schemes to memory when you write the data to memory, some amount of data. Maybe it's 256 bits of data. You compute the ECC code for that data before you write it. You write the data along with the ECC code. When you read the data out, you recompute the ECC, you check the ECC. If it doesn't match up, you go into some correction flow, you figure out the right data, make the correction, write the correction back to memory, and continue execution. So that's generally the approach for memory. Other approaches for protection, rad-hard cells are your big hammer. Mostly it's the flip-flop states that we're worried about because those are holding values. They're more susceptible, more likely to impact functionality. You can have cells that are just more robust and less subject to flipping. You can use those cells if you can accept the area impact. Redundant logic. So if you create two copies of your logic, whatever that logic is, and one copy behaves badly, they produce different results. It's kind of like our miter circuit, right? You have two copies of the logic, you compare the outputs. If something is wrong, you've been able to detect an error. Can't correct it. If you have three copies of the logic, now you can vote. Two of them agree, one doesn't, you can correct. Obviously, that's also very expensive. Also, back to memories, right? You often, you have various issues with memories. You might have aging issues where the memory just over time becomes less and less reliable. So when you have these ECC schemes, you also might be keeping track of which memory location went bad and you can sort of squirrel all this information around and periodically analyze it. If you figure out that a certain region of memory is just reliable or a particular address is unreliable, you want to be able to swap that address out. So you can also play games there with, you know, either blocks of memory or redundant memory that you can swap out for individual addresses to deal with those aging issues or manufacturing issues. Okay, again, the point I expect you're going to walk out of this room with is, oh my God, this stuff's complicated. Yeah, it's complicated. Design for test. So test, the main one I'm going to talk about here is built-in self-test. So this is for array structures. The idea with built-in self-test is that you can power on the chip, run BIST on all the array structures, and it will self-check the reliability of that array structure, memory, or you know, whatever technology is used for that array. So BIST, the nature of BIST, well, I guess it's not just arrays, but first arrays. So, for example, cycle through all the array indices, try writing, you know, various patterns, all ones, all zeros, 1 0 1 0 1 0, 0 1 0 1 0 1. Make sure you can write it, make sure you can read it. Do different access patterns of writing one address, write the address next to it, make sure that doesn't mess up the values. And you can do all that in a regular way driven by logic. So you power on the circuit, it goes through its automated testing, driving these patterns through the array structures. If something goes wrong, it'll tell you. With random logic, you can kind of apply this boundary scan approach, right? So if you have scan on the inputs to some logic, you can shift in a test vector, single step to apply that vector to the logic, and then read the outputs and compare with an expectation of what those outputs should be, right? So that the inputs and then the testing would be referred to as vectors. You're applying one vector after the next to your logic to make sure that it's functioning correctly. So you can use these techniques to sort of self-test your silicon, make sure it's healthy. Any questions about all of that, especially the post-silicon methodology? Again, I don't expect that you can go off and implement DFD functionality for a complex piece of silicon, but I want to give you the general impression of what's involved with designing for debug, designing for test. Okay, a bunch of slides on, in particular, the open source tool flow that we're going to use, or that's used by Tiny Tapeout. So this is Open Road that's provided by eFabless, that's wrapping together various open source tools into a flow, push button flow. These slides are not mine. They're courtesy of Mohammed Shalan, who works closely with some of the eFabless guys as well. So let's see. So basically going into the ASIC design process, right, we need, is there a question? We need the EDA tools to support the work. I mean, basically we've been looking at the process of generating the RTL, right? Now we're primarily looking at the tools that take us from RTL to the collateral that we need for implementing the ASIC, for taping out the ASIC. So we need the EDA tools to support the process. Our design, you know, likely is using a bunch of design blocks that we didn't design ourselves. The industry has adopted this horrible term IP, intellectual property, which is a legal term. Why we're applying a legal term to an engineering concept, but it's just the block of logic that we're leveraging, right? And this tends to be the unit of intellectual property when you're talking about design teams, is why the term is used, but I don't like it. So you might get open source IP blocks from LibreCores, OpenCores, GitHub. LibreCores, so OpenCores came first. LibreCores kind of spawned off of that from folks who kind of like their own direction. LibreCores kind of declared that the community had become successful with GitHub, and GitHub was the repository for everything. So basically, GitHub or GitLab or any other Git host to get your open source IPs that are part of your design. And then there's the PDK, that's the process development kit that defines the technology that you're using to implement your circuits. So these all come together to feed the process of developing your ASIC. And then, you know, our flow, we're looking at Skywater. Google was a part of this for a while. I think they've dropped out at this point. But Skywater is our 130 nanometer fab where your designs will be shipped. Global Foundries was also in the picture for a little bit with their 180 nanometer technology. This slide says Sky 90 is coming soon. This slide is kind of old. I haven't seen Sky 90 yet. I'm not sure what happened there or if that's still coming. Okay, a lot of stuff involved in physically implementing the RTL that you write, right? So a lot of different tools. We'll take a look at the big picture of how these work. So first of all, I'm not the best person to go over these slides, but I think at least at this level I can explain these different steps. My focus is all RTL and above, ones and zeros. Here we're looking below that. So your RTL goes through logic synthesis to become the gates that define your functionality. Logic synthesis goes, I'm going to take a look at the next slide. Okay. Logic synthesis, after that, you're doing floor planning and power planning, which is how the logic is laid out in the silicon. So synthesis is focused on the cells that are used to implement your logic, whereas this step is focused on where those cells are going to be placed and how the routing is, no, not the routing. Let's stick with the placement of the cells. Actually, that's not true either. That's here. So floor planning, power planning. So power planning is kind of the layout of the power network that's delivering power to all of your logic. Floor planning is the organization of the logic across the chip. Place is more cell level, where is every cell going to be dropped. Then you factor in your process development kit. And so this is characterizing the technology that you're using to implement your physical circuits. So what is the, you know, what are all the metal layers? What's the metal stack look like? Your cell libraries, all that. So clock tree synthesis is how you're delivering your clock to all of your logic. Routing, so you've got your cells at the lower level, metals, and you've got your interconnect above that. So routing is all these upper level metals that are connecting up your cells. And after you've got everything kind of placed, you have your physical design defined, you go through some checks to make sure everything is kosher and sign off on it. The output of this whole process is GDS2, which spilled over into the next line. That's the data file that you send off to tape out your design, send off to the fab. So we'll look at each of these in one level more detail. So logic synthesis, the input is your RTL. You go through logic synthesis and generate kind of gate level or cell level of your logic. So SCL is a standard cell library that characterizes all of your cells. floor planning and power planning. So here you're defining your ins and outs, where they go, the overall placement of things on the silicon physically, such as this, right? So my CPU logic is going to land here, my SRAM is going to be here, and what all the interconnect is between these. I'm not sure what's coming up here. Placing the IOs, I guess. So this would be power planning. So how is power being delivered to the silicon, and how are we distributing that power throughout the silicon? So power and ground, right? VDD and VDS, VSS. We will see this, you know, when we looked at the 3D flyover view of the ASIC, right? We saw the high-level metals, the big rails on top of the chip. Those were the power lines. Placement. So here we're going from what came out of logic synthesis, the logic blocks, and physically placing those to fit the grid that's defined by our technology, right? We have some sort of a grid that the cells must align to. And so here we're dropping our inverter, our OR gate, our AND gate. We haven't yet connected them up. That comes later, and our flip-flop. So these are our, you know, each of these is a cell from our standard cell library. We're playing with Legos here, fitting that to our Lego grid. So there are multiple steps in the placement process, right? You're starting very high level, and you can sort of picture a bunch of cells connected by rubber bands, and you're stretching that network out to connect it up to the outputs, and then everything just sort of has to kind of fall into place into open space. So you start out with very rough placement, and then kind of refine that down to more specific placement. Clock tree synthesis, the network for the clock. So the trick here is generally the way this is looked at. I have opinions here, but anyway, the way the tools work, they're trying to deliver the clock uniformly to every cell to the extent possible, right? You want all of your logic to see the clock edge at the same moment in time. Obviously, it's not going to be perfect. There will be what's called clock skew, the difference in when one piece of logic sees the clock edge versus another piece of logic. But the goal of clock tree synthesis is to create a network that's delivering that clock in a uniform way across the silicon. And to do that, we usually create structures that look something like this, which for what I hope are obvious reasons is referred to as an H tree, right? You can see the H at the top level here. You know, this H sort of as a fractal, break that H down into the next level H, flipped on its side, break that down to another H. This way, the path to every one of these leaf cells is the same distance. So the skew, you know, you can keep the skew minimal that way. You can also take an approach that's more of a grid. I don't know if I have a picture. I don't. So a grid clock, you can, so if you take this path around versus this path around, these guys are next to each other, but they've taken a very different path. So you've ensured that the two paths are close in length, but since they're different paths, they could still be a little bit skewed. The idea of the grid clock is basically to connect these two up. If there's a little bit of difference, you know, the clock edge kind of bleeds from, maybe this one gets here first. If they're connected, the clock edge bleeds over this way. You can minimize skew that way further. So grid clock obviously is more of a grid than an H tree like this. So after clock tree synthesis, you know, you sort of let the clock tree use some of the upper level metals and then do the more detailed routing with what's left. So detailed routing is connecting up all the individual cells, figuring out, you know, where do you need to use upper level metals versus lower level metals. The upper level metals are faster metals because they're wider, so less resistance. All these things have to be taken into consideration. So you start out with global routing, doing the large, you know, long distance routes in the upper metals, and then fill in the more detailed routes. These processes are a little bit iterative. Depends how the tools are designed. I can't tell you all the internals of the algorithm, but you know, you kind of try things out, make adjustments. Certainly lately there's a lot of experimentation with AI-based algorithms for routing and as well as logic synthesis. After you have your design, you want to make sure, you know, this is kind of the verification step to verify that the tools did what they're supposed to do. If the tools are all working and doing their job, the check sign-off shouldn't be an issue, but we want to check the tools. So we do various back-end checks after we have this. And then we have our GDS2 file, which we can send off to get fabricated. So forms of physical verification, various design rules. You know, a design rule might be something like between this layer of metal, there has to be at least this much of a gap, or I don't know, I'm not a physical guy, but all the constraints that you have to physically meet when you're using the physical resources of the silicon. And, you know, as I mentioned before, we do layout versus schematic to verify the layout versus the schematic. Timing verification is the process of analyzing the timing statically. Shock. So, you know, you're analyzing the delay on all the routes. As I said, the upper level routes have less delay than the lower. For the same distance, you're analyzing the delay through the cells. So all of these things are characterized with a static number that represents the kind of worst case delay. And you're essentially just adding up all of these delays to make sure that every path in your model meets the required timing. What is this slide about? It's about nothing. I thought I deleted this slide. It's a complicated process. It needs methodology and flow and tools. So OpenLane puts all of this together so we can just upload our RTL. The GitHub action kicks off the OpenLane flow for us on our designs, and all of this just happens. So this is just depicting that flow, right? Which is similar to the last picture we had, but the RTL goes in, it goes through synthesis, floor planning, place and route, clock tree synthesis, routing. We get our design out, we get our GDS2. A more detailed picture of the same thing, right? I know you can't see it. I'm not going to go over all of it, but just to give you the impression, there's a lot of detail going on with all these tools. You know, all of this coming together has been 30 plus years of open source contributions to all of the individual tools, and now finally coming together as a push button flow. So there's a lot of human capital behind all of this work, all in the open. So we have a lot of people to thank, and I unfortunately don't know all of their names. When we do design, right, it's pretty rare that we're designing anything from scratch, starting from nothing and coding up all the RTL for the whole chip. The methodology today is basically you have teams that are working on IP blocks, and you have teams that are building chips by integrating these IP blocks together and maybe adding a little of their own secret sauce. The IP can be delivered in two main ways, soft or hard. Soft IP is delivered as RTL. hard IP is delivered as, for a particular technology, maybe delivering the GDS2 file for that IP. So when you're bundling IP to deliver to a customer, you're bundling the GDS2 file with all the polygons that are physically going to be stamped out. You're delivering these left files that have the physical interfaces so that you have the information to connect up other blocks to this IP. Liberty files contain the information about the timing. The RTL, of course, you can deliver along with GDS2 for functional simulation so that your customer can integrate your RTL with the rest of their RTL and simulate their designs. You might deliver the RTL in a way that it's encrypted so your customer can't see it, because this is your bread and butter, your secret sauce. You don't want to reveal your secrets. I think several years ago, the encryption standard for RTL was cracked. You're also delivering documentation, of course, verification collateral so that your customer can verify what you deliver to them. Corner models would be, and I don't know exactly what form this takes, but process corner would be sort of when you're physically fabricating your silicon, right? Some silicon is going to come out with certain characteristics, and sometimes you're going to come out with other characteristics. So the corners are covering the extreme cases of the variance in fabrication of the design. So this would be collateral that you deliver along with your design that would help your customer to do the analysis at different process corners. And other physical verification collateral, so the design rule checks and so on. Honestly, I'm not very familiar with the forms that these would be delivered in. Yeah, I mean, I would think it's the same design rule checks that you would apply everywhere, so I'm not sure why it's associated with the IP. I don't know, you might know more about it. But anyway, soft IP, you're delivering fundamentally the RTL, so hopefully well documented and commented RTL if it is visible to your customer. You might also be generating the ability, you might be delivering generators of the RTL. Your customer might want a certain configuration of your design. TL-Verilog is helping with that, right? The TL-Verilog itself has mechanisms for configurability that could be valuable in this context, but generally RTL itself is not very configurable, so often folks delivering IP will develop their own tools to help customers be able to configure the RTL to their needs. Verification collateral like test benches, stimulus reference models, checkers, formal verification collateral, input constraints, right? Properties on the constraining the inputs of the model, right? The customer is going to tack on their own logic. There's a certain API to interface with the logic that you're delivering, certain constraints on what the customer should be allowed to provide as inputs. You want to deliver the properties that provide those constraints. Those properties are used in two ways. First of all, they verify that the customer's surrounding logic is behaving, and then they're also used as assumptions for the verification of the IP itself. You might have high-level models, like a System C model, that goes along with your RTL that the customer can use as a more abstract model representing the behavior of the system you're delivering, the circuit that you're delivering, so they can do faster simulation of higher level models. Docs and visualization, visualization in particular, something that I'm trying to change the standards here, right? It's not standard that you deliver visualization with your models today. I think it should be. with the visual debug feature, that's something that you can do. Yeah, so timing constraints on the IOs of your model that can then be used by static timing analysis tools. Again, that's kind of the boundary. You use those timing constraints to verify timing of the logic itself and to verify the timing characteristics of the surrounding logic. IP exact is a methodology for integrating IP. So the IP exact standard defines formats for specifying interface properties of your IP to help with the integration of that IP with other IP blocks. So things like what registers, control and status registers, are supported by my IP. Undoubtedly, you're going to drop into an ecosystem where there's mechanisms to read and write control and status registers. And you need to define what those control and status registers are in a way that the overall system understands, your control and status registers as well as the rest of the design's status registers. Bus protocols, standard interfaces to your module, things like AXI protocol and things like that. Yeah, so along with, bundled in the IP exact collateral information about how you can parameterize and configure your design. Any questions on that before I move on? So just a couple slides on technology trends. The bulk of my career, computing was all about CPUs. Right? The world is changing, and I think that's very exciting. We kind of beat CPUs to death. Technology trends actually took us from a time period in the, going from the 80s to the 90s where we were throwing every technique we could possibly imagine into the CPU to get the most performance per cycle possible. We created these very big, and when I say we, I mean myself included, was a part of this process of making CPUs incredibly big and clunky and complex. This gave us sort of percentage improvement over in performance, and that gave companies an edge. It also burned a lot of power. So some of the technology trends have taken us to a point where, first of all, power is a first order concern. Power impacts performance because you have a certain power budget. If your one core is burning a lot of power, you need to cut back on that by slowing down the clock and things like that. So everything is related. So these big cores were power hungry. The technology trends sort of pushed us to a place where interconnect delay was more substantial than the delay through logic gates. These big complex cores, since they're big, they have a lot of routing, a lot of delay from the routing. So those trends sort of pushed us back toward tighter, more compact cores being more performant. So the industry overshot. We made these cores that were too big, too power hungry, too complex. So all the innovation in CPU architecture for the last decade or more has been, what are we going to throw out? And people are writing research papers about this brilliant idea to get rid of this idea from yesterday. So I'm very glad to see a lot of new opportunity for not for CPU microarchitecture, for computing platforms, right? So FPGAs are becoming more of a force. FPGAs are kind of a form of abstraction, right? We can't afford to be doing these monstrosities of ASICs. We need faster turnaround. FPGAs we have less control over, but we can turn around the designs faster, innovate on architecture faster. So over time, we're sort of forced into these more abstract design approaches, and FPGAs are more relevant. So DSPs for signal processing, GPUs then, around late 90s, 2000. we started using GPUs not just for graphics, but for general purpose computing, right? So GPUs were the architecture that was highly parallel, where your computation is not as flexible as with the GPU, but you can do computation in parallel. So initially with graphics, but then that same architecture was good for other forms of parallel computation. I mean, as we get more, as hardware generally becomes more performant, our applications scale and we're working with larger data. As we work with larger data, that means we're doing more computation that can be parallelized. And so these parallel architectures become more important. So GPUs being one of those, and then, well, okay, so I guess I have my timeline marked here. So GPUs for graphics was late 90s. GPUs for general purpose computing sometime in the 2000s. And TPUs more recently for, for AI and neural computing. So different terminology for things in a similar domain, right? Tensor cores, neural processing units. More recently, I would say, an emphasis on intelligence in the networking, in the routing functionality and processing data, steering data. So you've got terms popping up like data processing unit, infrastructure processing unit, network interface controllers, smart network interface controllers. The idea being to generally to make the network itself more programmable, having the protocols that the networks are using being programmable. When a new network policy or network protocol comes out, you want to be able to reprogram the existing hardware and not have to generate a new generation of hardware. So more flexibility in network routing of traffic. Coming down the road sometime in the future, quantum. Who knows what that will look like and when. But, the exciting thing here is just that if I cover this all up, my world coming into it was just CPUs. And things have gotten interesting. I think this is a really exciting time to get into this industry. Looking at CPUs in particular, right? Moore's law keeps us on this kind of linear number of transistors growth. We were focused on single stream performance for a long time. That has tapered off. Frequency, there was kind of this push to get to gigahertz, and then once the marketing had been accomplished, that kind of leveled off a little bit, and there's also kind of a wall there in terms of complexity. I would say this trend is driven more by marketing than anything. No, marketing used to all be about megahertz, gigahertz. Now that's not really a concern. Power, has continued to grow, but gotten to the point where it's more the limiting factor. So we have to put more emphasis on capping power. Number of cores for processing, right? For a long time, it was all about single stream. Now we're looking at, chips that have hundreds of cores. One current trend that's going to be very important, right? So again, it's all about abstraction. So how many layers of abstraction are in the process? As things scale and get larger and larger and larger, eventually the existing stack of abstraction levels breaks and you need to introduce a new level of abstraction. That's what chiplets are all about. So where we used to have a single chip, we now might have a multi-chip package where we put multiple chips together. We slap an interposer on top, which is a chip that has all the routing to connect up the chiplets. And we kind of slap that over the chiplets to connect them up. I kind of like this zero ASIC model that defines the chiplets as Lego building blocks, right? So they're taking this concept of chiplet and defining a very clear standard for the, the size of the chiplet protocols, so different chiplets can talk to each other, so that you can mix and match standard chiplet components. They have this little environment where you can drop chiplets called e-bricks of different types. I want a CPU, I want an FPGA, I want an ML accelerator, and you can drop I/O components that have different I/O capabilities and build yourself an ASIC. Okay, this is a fairly young company. It's new and evolving technology, but I think this is a good view on the concept of chiplets. Questions on any of that? So flows and methodologies. So we've been using transaction level Verilog. This will get us into sort of understanding a big picture, what is the motivation behind transaction level Verilog, and what are some of the related technologies and the differences among them. So just a depiction of how the design process evolves. So, I've said we really don't do clean slate design anymore, but this would be the picture for a clean slate design process. So you develop early RTL that is fairly abstract. You start building your verification environment, so you have various models that are connected to that RTL. You start you have your spec evolving, and you do higher level models for performance and function and power. Over time, you are evolving this model. You're introducing additional verification collateral, all connected to the same RTL. Your verification effort is focused here on this RTL, which at this point is still fairly abstract. Over time, you're working with your implementation team on how you actually implement this behavior. You're incorporating more and more physical detail, right? So what is the exact partitioning of the logic that I need to implement? What are my synthesis blocks? I need to have modules exactly at those boundaries. So I need to be, very explicit in my RTL code about exactly what signals are on one side of the module boundary or the other side. I need to work out all the timing issues that we've discussed when designing the CPU core. So if there's some functionality that isn't meeting timing, you have to make the appropriate RTL change, as we looked at. You might be messing around with the encoding of signals to optimize the implementation of your state machine. Maybe you need to take a state machine where the states are encoded values, right? If you have 8 different states in your state machine, maybe you originally designed that with states that are encoded as 3-bit values. Timing's not working. You can optimize that by doing one-hot encoded states. So you encode them in 8 bits instead of 3, and only one will assert at a time. That's something that tends to reduce logic depth. So all of this change is motivated by physical constraints. It represents churn in your model. It represents detail in your model. So you end up with code, RTL code, that incorporates this physical detail that we refer to as physical RTL. I don't know, that was kind of an Intel term. I don't know if it's used elsewhere. So as you're doing all of this, all of the verification collateral and debug collateral that's connected up to your RTL model has to stay in sync. So all these changes that you make to the RTL, anywhere there's collateral connected to those signals, to those module interfaces, that has to be maintained and updated. So there's a lot of churn in that process. Then the next generation design comes along, and you need to leverage the previous generation. Well, what you're leveraging is physical, and your next project needs to change a lot of those physical details, right? We talked about that with respect to timing. And there's, more aspects to that than just timing. So your next project comes along, and what you'd like is to get back to the more abstract model and then be able to incorporate different physical detail. It's a tough challenge, right? All the verification collateral is connected with all this physical detail. So you end up making a lot of the change at the physical level and maintaining all this detail that was accumulated in the last generation. And toward the end of my career, some of the tech leads did some analysis and discovered that roughly 70% of the work that we do to get from one generation to the next generation is just mapping the old generation to the new technology with new constraints. So the remaining 30% was actually focused on implementing new capabilities, new functionality. That remaining 30% was very unproductive because we're doing that at the, with all of this detail in place. So these are some of the problems that TL-Verilog was meant to address. So another look at this today, our design methodology is, again, things get more complex, you add additional layers. So as things got more and more complex, more and more we're doing this SoC design, which is pretty much the norm across the board now, where you have teams that are developing the IP building blocks and you have teams that are integrating those building blocks. So even within a company with internal IP, the IP that you're developing is delivering into multiple products. So, so here we're looking at a bunch of IP teams developing different RTL building blocks, and then a bunch of chips using those building blocks. So the same RTL, the same HDL models are delivering into designs in different contexts and have to satisfy the needs of all those different contexts. So when you're doing that, right, you're building Lego blocks that are meant to be generic and aren't tuned to any particular set of constraints. These different environments have different requirements for area, power, performance, different test and debug infrastructure, different clock frequencies, different feature sets, and different product requirements. So, so you lose something, right? I mean, we don't have many products in the real world that are sold that are made out of Legos. In the hardware world, we do have products today that are built out of Legos, but you certainly give up something when you do that. I think, let me see how much else we have left here. All right. So if you don't mind, maybe we'll go to 6. I'll try to wrap these up, and then tomorrow we can start fresh. Is that okay? I think especially also since tomorrow I'll be leaving early. Maybe we'll go a little bit longer today if you guys are okay with that. All right. And then tomorrow you can wrap up a little early, probably 5 o'clock. So we want to be able to design at a higher level of abstraction so that we can shelter ourselves from all this gory detail in the physical RTL, right? And so we can verify these models that are higher level and more stable. Sorry, let me just check my slides. Okay, I was just making sure I didn't do this because I've presented related material so many times this week. I feel like we've already been over it. So we want to get to a higher level of abstraction to increase the stability of our designs through all of this churn. The industry, so there's various, I'll divide things into 3 general camps of activity, right? I mean, every approach is different and unique in its own way. But general buckets, the EDA industry is highly focused on something called high-level synthesis. This has evolved to be based on C++. Fundamentally, it doesn't need to be, but that's become kind of the standard. So this is using C++ to model algorithms and very sophisticated tools to map those algorithms to hardware implementations. And you can provide attributes that guide the physical implementation to generally be correct by construction, although there's some imperfection there. So generally, you're synthesizing algorithms to RTL. It's a nice ideal. Generally, what you find is, I mean, this works out well for teams that are software teams that are working with C++ designs, and that's their starting point. Then how do you get from that starting point in C++ to a hardware implementation? High-level synthesis is a tool that can help with that. Generally, what you find, though, is you may be a bit naive going into it, thinking I just take my C++ code, I push a button, out comes a hardware model, and my algorithm runs faster. Generally, by the end of it, you've become a hardware engineer, and you're essentially writing RTL using C++. Lately, there's been emphasis to kind of go even beyond that so that you can write models that you can target to different hardware platforms, whether it's running in software or running on a GPU, running on an FPGA, compiled for an ASIC. The academic focus tends to be on domain-specific languages. So this is taking an existing software ecosystem and applying it to the problem of hardware design. So just about every major language, software language that's out there, there's at least one domain-specific language for hardware that's layered somehow on top of that language to provide hardware design capabilities. Yeah, I guess I'll leave it there. So transaction level Verilog sits in a relatively unique camp. I'd probably lump BlueSpec into a similar camp of a language that's specifically meant for hardware with abstraction mechanisms that are specifically meant for hardware, using abstraction as context to specify your details. So in the interest of time, I will skip over that. We'll wrap up here. Tomorrow, we'll focus on your final projects. So I have a couple slides just to give you some ideas for final projects. We'll brainstorm about what we're going to do and have some fun, right? This is where you take everything that you learned in the first week and have the freedom to use those skills to do a project that excites you. Anything else you want to add, Srinivas? Alrighty, so we'll see everybody tomorrow at 9:30.
So when you come on Thursday, just